Hold on. It's not going to show the slides. So let me just add them again. All right. So before we start, I'd like everyone to go to their notifications and sound settings. So if you can go to the purple background with white X mark on your right lower corner of the screen, kindly click that part and click on the setting or the gear icon. You can see that. And then it will show or it will open a side window that says notification settings. Please go ahead and uncheck all the boxes in your notification settings so that you won't be distracted with all the notifications that would pop up your screen and you can focus on the webinar. Okay, so if you are done with that, kindly give me a thumbs up or a smiley or a yes if you are done with your notifications. Okay, some are saying done, and I hope that, thank you so much for your responses, guys. I hope that everyone will do so just to ensure that you would be able to focus on the lecture later, okay? All right, so thank you so much for attending today, everyone. We are very glad that you are here today. And my name is Lisa. I am one of the course advisors at AIT, and I'd be hosting the webinar today. And it is about the computational simulations of wind flow patterns around buildings. And it will be our lecturer today would be Vijay Kumar Veera, and he is one of our lecturers and course coordinator in mechanical engineering courses at EIT. And of course, just a few reminders for you guys. So these are the most common questions, and I'll just go ahead and give you the answers now. So if you need a copy of the slides or a video recording of the webinar after this session, then normally we would be sending this in 1 to 2 business days via email. But since we are going to have a long weekend starting tomorrow, this may be available on Tuesday, the latest. So our team would be sending or sharing an access of our slides and PDF slides and video recording as late as Tuesday next week. Okay. And if you'd like to download the material, you can also go to your upper right corner of the black screen. There's an arrow down with a half box there. You can also click on that to download the material, okay? And for your certificates as well, we provide a free digital certificate of attendance for those who attended live today. And later on, by the end of the webinar, I'll be showing a QR code and sharing a link so that you can request for your certificate by filling out that form. And please note that we usually close we have a cutoff for webinar certificates, and that usually closes on a Sunday night, which is going to be this coming Sunday evening. So please make sure to use the QR code or use the link on or before Sunday evening, right? And let me also give you a little bit of glimpse about or some important facts about EIT. So we are an engineering specialist school, and we are one of the only institutes in the world who specializes in engineering. And we have a variety of courses from professional certificates that are designed for professional development. We also have diplomas, advanced diplomas, undergraduate and graduate certificates. bachelor's and master's degree, and a doctor of engineering degree as well. And of course, we make sure that our programs are industry oriented. So they are designed by experts of the engineering industry to ensure that you would, as a student, you would graduate with cutting edge skills. And of course, those are valued by future employers in any engineering work or industry. And of course, our program contents are current, and we make sure that they are also up to date with the latest trends in engineering. We are also accredited worldwide. So we have, of course, our Australian accreditation, and we also have programs that are recognized under the International Engineering Accord. So we have the Sydney Accord, the Washington Accord, and the Dublin Accords as well. And that is from Engineers Australia. And we also have industry experience lecturers, just like Mr. VJ here, your lecturer. He is one of our industry experience lecturers, and we make sure that they are highly experienced in their field so that they can share valuable insights with you during your lessons. And also, we ensure that our technologies as well are up to date and cutting edge so that you would have the best learning experience. And unique delivery models. So we have live lectures, we have on campus classes, we also have practicals, we also have our technologies like state of the art, hands on technologies like our virtual laboratories and remote laboratories to make sure that you are well exposed and you would have the best practical learning experience too. So that would be it about EIT, and I hope that you would take note of those. And we can now officially begin our presentation, and let's welcome Mr. Vijay Kumar Veera, and he would be going ahead and starting the webinar or the main lecture for this webinar. Let me just go ahead and send him a message just in case he could hear me. Uh, all right, here we go. So
Hi everyone, can you all hear me? For some reason, I was not able to listen to what Lisa was speaking. Lisa, thank you so much for the introduction, and apologies for this glitch. I have to investigate what's going on with my machine, which is causing this issue. But thanks everyone for your patience, and I'll just briefly introduce myself, and then we'll get started with the webinar. My name is Vijay Kumar Veera, and I have about 11 years of experience using computational fluid dynamics technologies to solve both industrial and academic problems. I have an MPhil degree in engineering from Cambridge University in the UK, and I have a master's and a bachelor's degree from Indian Institute of Technology in Bombay and Madras, respectively. And I currently work in Sydney, and I also have a role as a unit lecturer and course coordinator at EIT. I I undertake uh, MME 506 and 604 units. MME 506 is Introduction to or Advanced Fluid Dynamics, and MME 604 is Introduction to Aerodynamics for students pursuing their masters in mechanical engineering. I have a passion to teach computational fluid dynamic techniques, and hopefully I can show you how we can use these techniques for doing interesting problems in the realm of understanding flow patterns within buildings. So I'll move forward. So I think we've finished our welcome and introduction from the agenda. I'll go on to the next slide, which details the challenges and in the design of buildings and how computational fluid dynamics can help. And then we'll go over a brief CFD simulation methodology. That's a template which is useful for any type of CFD simulation you would do. and then we will and then move on to a hands-on demonstration to show how I would go about solving a problem on understanding flow patterns around buildings. And then the pressure, and then from there we will extract the pressure contours, velocity contours, and show some flow patterns to understand what's happening to the flow as it moves past the building. And then at the end we have conclusions and Q&A. Okay, so let's move to the next slide. So do you guys know what is this image on the right? Which building is the image on the right? So if you let me know if you can guess that. But while I wait for some, okay, yeah, Brian has said it's the Petronas Twin Towers. It's one of the iconic buildings in the world. So some of the key challenges of building such a big structure is that these buildings will have a lot of structural loads acting on them, and that's because of the way the wind has to move around them. So you have a you have a natural wind phenomena for this region. So there's the wind climate for this region, and there is a tendency of air to flow in a certain way. Now when we built this big tower or big or twin towers, then the wind has to find other paths to uh, go past. So it has to, and what we will see is it won't just all regions. So for example, wind at the lower base levels of the tower will not move in the same direction or will not get displaced in the same way as wind in the upper edges of the tower. And that's where computational fluid dynamics comes into its own. You can visualize these wind patterns before you even build a tower like this. Also, I'll give a fun fact in terms of structural loads. Uh, so, I guess most of you know the world's tallest building, which is the Burj Khalifa in Dubai. If you look at the tower itself, or if you research into the tower itself, you'll find out that top few floors, maybe top 10 to 12 floors of that building are actually not habitable, so nobody lives in there. And the reason is those regions, because it's so high up in the air, the because of the wind speeds at that height, the these floors will just keep moving about. So they'll keep moving about, and if you are staying there, you'll feel like your world is swaying all the time, and it becomes nauseous pretty quickly. So but then you can once you understand what is causing this kind of wind motion, you can come up with strategies to solve these kinds of phenomena. And then people have done a lot of research in understanding what's causing these building induced motions, and they're hoping to apply those learnings into creating taller buildings in the same region. Yep. So, um, and also we have to look at appropriate pressures on the surfaces of this tower. So, when the wind is moving past it, is it enough to, will, what thickness of glass is necessary to withstand these kinds of the wind loads? If you have too thin a glass, you'll see that it'll start shattering. And uh, and it might also, you might also need to design it for extreme wind events. What if there's a hurricane that is going through this path? It should, you don't want the whole glass panels, all those, to be shattered, because it'll take a long time to replace them. So next up is, how does CFD come into this picture? So like I said earlier, it is best place to quantify um, flow patterns in the a- and identify the new routes air will take to move past the building. There's also a, a part of part of analysis which is focused on wind comfort. So if you have been in a very dense city, you will and then if you're commuting from work or home to um, work and home, and through a dense city, you might notice that, especially if you're walking, you might notice that some regions are more windier than others. Especially if you're walking about in a city center, you'll see that some corners are windier than the other. And like for example, in New York and other places, there are streets which people will avoid because they're just too windy. And the reason they are windy is the heavily built up nature of say Manhattan or other places will create flows which get squeezed. As they get squeezed through buildings, they will have to accelerate, and sometimes they will accelerate and hit the ground or hit ground levels from higher up, and that causes these sudden gusts of wind, which will cause a lot of comfort issues. So CFD can be used to understand and identify these issues and mitigate them. So so this webinar provides an example on how we can quantify these flow patterns and say pressures on the surfaces of a building. So before and then we'll move on to the next slide, where we will discuss about how we'll go about it in the CFD simulation methodology. So first step in any CFD simulation is to create a virtual geometry of the problem you are trying to solve, whether it be flow past a building or flow past a car or flow past an aircraft. You need to create a virtual geometry and create and generate the fluid domain around the building. So I'll show you when we get into the demo. I'll show you how we do that. Then we generate a mesh that captures the regions of high interest in with sufficient resolution. Then we choose the appropriate turbulence model to represent the flow physics, and we specify the correct boundary conditions and choose the solver settings necessary to run the solver um, stably. So that's your mesh. This is usually called the pre-processing stage. So creating the geometry, the mesh, and setting up the case, that's called the pre-processing stage. And then you solve the governing equations, which are the Navier-Stokes equations, and these equations determine how the fluid will behave. And we solve it iteratively until there is little change in the solution. And once we have that, we visualize the flow field by plotting contours, vectors, streamlines, and animations. And this is how we see the various wind patterns that are generated by the building. Then if we have any experimental data, we can compare with available experimental data to evaluate the efficiency of this CFD model. And then when we compare with experimental data, we might have to go back and change some regions of the mesh. They might be under resolved or over resolved. So you go back and sometimes you have to repeat this process until you get a good comparison with available data or with a solution that you are that is reliable for you. So now let's go into the first step of of this simulation, which is to create the geometry. So what I've done is, obviously I can't simulate the twin towers in front of you, especially in a 1 hour webinar. And so what I did is I just created a simplified design where it's about 10 stories high, and there's a shared podium across these, and there are some insets into this building facade which serve as balconies. And this is like a typical apartment complex you can think of with 10 floors. So this is not very uncommon. So what we'll do is we'll look at the flow past this kind of a structure, and and then we'll see how we can use we use a software called Ansys to solve this problem. And the reason I chose Ansys is because it's one of the biggest software providers over there, and um, there is a student version that you can download for free and install and follow this recording, and then you can probably reproduce this simulation. Okay, so with that, what I will do is I'll start sharing my desktop screen. So I'll just do that now. um, Screen share. So let me know when you can see my screen. Sorry about that. I'll just keep this somewhere here. Okay, I think you should be able to see my screen. So this is a tool called Spaceclaim within the Ansys suite. And what Spaceclaim does is it will allow you to create geometry from scratch, or you can create or import geometry from other CAD software. So what I've done is this is an example of a building. So for example, this is a level. So I have scaled it up a bit so that it's easier to mesh. Um, here each level is I've set it as 20 meters, but usually it's around 3 meters or so. And then there's also a balcony which is about 15 meters deep. So this region can be would be balconies across the building. And then this is a podium, and this could be, you can have like a railing here and here, and you could have like a region, you can have different things here depending on where this building is being constructed. If it's near the beach, you can orient this such that people who are sitting here can have nice views to the beach. Suppose this is near a rocky region, you can again have some seating area or some playground kind of a thing, where which overlooks mountainous views, all that. So this is an example of the geometry. What we have to then do is we generate a fluid volume around this, and to do that, what we will do is we go to the prepare tab, and in the prepare tab there's an option called enclosure. So what that does is, if you read this, it says select one or more bodies to create an enclosure and click the check mark to complete the enclosure. So what this has done is it has created like a box around this which encompasses this building. So I'll change this cushion to be, say, 100, um, or maybe 50, and then select this again. And then if I click on the green tick, what will happen is you can suppress this for physics. And what it has done is it's created a geometry. This is the fluid domain where we have the body, we have this, which is the body of the building geometry. Then we can have the flow inlet like over here, the flow outlet over here. These two we can assume are symmetry. Here we are looking at flow just hitting normally, or flowing normally to this building. This can be the sky. And what we have to do is, um, we don't want, right now this building is suspended in thin air. We want this to be the ground, which means this has to line up with this surface. So what I do is click on the pull tool, and then there's this option to pull it up to a given surface. And if I click like that, you'll see that this is the ground surface. Okay, so that's how you generate the domain. Usually what you have is you'll have the fluid domain which will be about 50 times the length of this building. So suppose this building, if I click on this edge, it says this is 400 meters long. This would be about 4000 to 5000 meters, so 10 to 15 times larger than the building size. Okay, so but for ease of computation and for showing this in the webinar, what I've done is I have an enclosure already done, where so if I hide this, I've already done this enclosure for you. And there's the next step is to identify your named selections, or you have to identify the boundaries through which air will come in and air will leave. So here I have inlet coming. I've selected two faces to the inlet, but I'll just um, replace that. So have one inlet and then one outlet. So I'll hide this and then replace that. So this is my inlet, this is my outlet. I will set these three faces as symmetry. Replace. So these are the symmetry faces, which means flow cannot go through them. It'll just go tangential to them. Sorry, let me just check if there are any messages. Okay, I will give a link to where we can download the software, and we can also import a Revit model into Spaceclaim for geometries. I'll just quickly check if there's any. Okay, any other questions? Yeah, just put them in chat, and I'll wait every 5 minutes and then answer them. So this is our ground geometry, and then these are the balconies. So these are all the balcony regions that I have identified. And then we have the roof, that's the top floor, and then we have the podium. So right now I have not modeled the railings. So generally you'll have railings around them. We have not modeled them, but because that's an additional expense. But once you know how to do this problem, you just add the railings and you can do it. So that's my geometry done. So let's just save this. And So this suppress for physics will, what it will do is it will prevent that object from being sent to the next downstream component, which is the meshing. So the way to invoke meshing is through this Workbench tab, and then so in Workbench there's an option called watertight geometry workflow, and then click start, and it will open Fluent for you, and it'll give you like a step-by-step procedure here to generate the mesh for you. If you just clear all these steps, at the end you'll have a volume mesh, and it's a very intuitive method for setting up the problem. So what I will do is I will generate a mesh with say 8 meters as the minimum size and 64 meters as the maximum size. Actually, I'll add local sizing, and um, that is to so if I just go here, and so that this local sizing is to refine the mesh in a certain region. So these balconies, I want to have a mesh sizing of 4, and I'll click add local sizing. There's an option to look inspect inside, and then if I select balconies, it's, you see it's showing up in green. So that green is where the sizing will be applied. So what that will do is it'll create triangles which are 4 meters by 4 meters in size. Okay, so now I'm ready to generate the surface mesh. So I'll just set 3 cells per gap. So what that means is between this edge and this edge of a balcony, the software will try to apply at least 3 cells. So once that is done, I'm generating the mesh, and usually this should not take too long. So there you go. So it has done about 100,000 cells in about less than a minute, 0.12 minutes. So that's 10-15 seconds. Okay, so what I will do is I'll create a limit in y. So that's your mesh, how it's looking like. You will see smaller triangles here on the balconies, and then slightly larger triangles here around. um, and then next step is so this is good enough. Generally you look at this quality of and if it's below zero point 0.7, that's good. So this green tick indicates that mesh has succeeded in create is it succeeds, or it has a good quality. If it was not good quality, it would have a asterisk on top of this. But right now we have a good quality mesh, so we can move forward. The next step is to explain to the software what kind of a geometry you are giving it to mesh. So in this case there are 3 options, and this is a multiple choice answer. There's only one correct answer for this. So you can look at this by elimination. So the geometry does not consist of only solid regions. This is actually a fluid region that we are simulating. The fluid around the body, the building, is what we are simulating. So the first answer is wrong. The second is it consists of only fluid regions with no voids. This I'm not sure. So I'll look at the third one. It consists of both fluid and solid regions and or voids. Voids are empty spaces that you don't mesh. Right now I don't have a solid region because this is all hollow. The surface of the interior of the building is hollow. You can see this. That's all hollow. And the reason it's hollow is because we are only interested in flow around the building, not through the building. So this is also false. So only the second option is correct. Okay, so next options for this problem, you don't have to do anything, but this is if you have multiple fluid domains connected to each other. So these leave them as default and click describe geometry. So the main thing you need to understand is this, which is the right answer in here. Next is to update the boundaries. So depending on the names you've given, the inlet and outlet, Fluent already understands to assign a particular boundary type for it. So all these, so balconies, ground, roof, podium, all these are wall boundaries, which means flow can't go through them. Flow can only come in through the velocity inlet, which is this one, and then or velocity inlet is this one, and then uh, the pressure outlet is the one on the right, or sorry, the left. And then I click on update boundaries, and then it's asking about regions. We have only one region, which is the enclosure, and that's a fluid region, so we don't have to worry about this too much. Then we add some boundary layers. So I will set this to be 5 layers, and then this transition ratio, again there's a question mark here which will explain what it means. Generally set this as 0.2, and that is, I'll show you what it means when we generate the mesh. It, so once, so I've added the boundary layers. Let me just check if there are any questions. Um, okay, there are quite a few questions. Okay, I'll probably go over this once we finish the meshing, or once I'm doing this meshing. In meshing, I'll just set a lot of those questions are really good. Thanks so much for raising them. While this is generating the volume mesh, I'll just see if we can answer one or two. Again, this is also going to be reasonably fast. This uses actually parallel meshing, so it's using 4 cores on my machine. So if you look at this performance, so have 8 cores, and then it's using 1, 2, 3, and 4. So these are the 4 cores it's using to generate the mesh. So and so you see this is heavily engaged, this is also heavily engaged. These are, it's going on and off, but we should, it'll print out how long it took. Okay, so it took less than a minute to generate 500,000 cells. But the thing is, the count is slightly more than what it wants. The hard limit is 512,000. So what I'll do is, there's an easy fix. Click on revert and edit, and I'll just reduce the number of inflation layers to 4, and click update, and then generate the volume mesh again. And that should bring us below the 500,000 cell limit. Let's just go to the, so you can import Revit files into Spaceclaim. Actually, if you look at file open, there's all these list of files you can import from. So there's um, Revit, there's Rhino, see. But if you have a complicated Revit model with all the nuts and bolts, it'll take a long time to import. Maybe you can bring it into something else like Rhino, which can handle that kind of large files. Okay, so then, okay, so ideally, Nick, to answer your question, implications of having a top boundary at a large distance. Ideally, you want your geometry to be the edges of the fluid domain to be much larger. I mean, they should be away from the walls of the geometry, and I'll show you when we do the CFD simulation. So for this to be a very good simulation, you want this face to be about this far. Okay, so all the faces should be about this far, or maybe at least this far. Okay, so that's because I'll show you that to you in the assessment. Then sorry, in the CFD simulation. Then next question is, can you edit materials to look at natural frequencies and vibrational influences? We can't do that, Liana. What we can do is, we can get the forces acting, pressure forces acting on the surfaces of this of the model, and then you can create a model, create a structural model in Ansys mechanical, and then apply these forces and look at do a model analysis to look at frequencies and vibrational influences. If you are a structural engineer who knows how to do that, you can just use this and then get an idea of these natural frequencies. And then the building is a void, Uma. um, that when you say void, um, we are not interested in the fluid inside the building. So we actually take the surface of the building and then create a fluid domain around it. Next one, Vincent, how do I know the right size of the mesh for higher accuracy? Generally, what you do is, you do what is called as a mesh refinement study, where you keep refining the mesh until quantities of interest like forces, moments, or drag forces, even like velocities of interest, velocities like average velocities in areas of interest, they don't change with any further refinement of the geometry. But the problem is, because we are limited by the number of cells, we can't do that. So right now we are just playing within the limits of the software. So right now we have a count of 488,000. So that's pretty good for us. Okay, let's see if there are any internal building pressures of the building. You can't. You can do the external building pressures. If you want to do the internal building pressures, what you have to do is you have to um, get all the HVAC flow system information. So how is the air coming in from? How is the air being pulled out from? What are the heating loads? All that. And then if you create an internal fluid simulation, you can do that. With this model, you can't. Then what is the relationship between the building form and wind loads? This one I'm not sure, Brian. What is the meaning of that question? Maybe if you can uh, explain that again, it'll be better. Then um, you I don't think MATLAB is a CFD solver, Nyoni. So I don't think you can simulate this, but you can do your own research. The one I'm more familiar with is with Ansys, which is most used for this kind of applications. Then, yeah, so the next question, what is the purpose of the floor? That's just to get the world record as the tallest building. So they're not occupied, but the building height is not going to change because they're not um, because people are not using it. Also, yes, we can combine heat transfer also. Suppose you have like solar radiation. This is all a glass facade. You might have experienced that on a hot day. If you're in a glass building without an AC, it will start becoming very hot very soon. So you have models that you can simulate that. So these are all really nice questions. Keep them coming. So I have generated my mesh now. Let's sorry. Let's look at the mesh. So if I just change the clipping plane, so this is my mesh, and then let me just go inside. Let's just not draw the cell layer. So these, you see these layers, those are the inflation layers that have been generated. And then, yeah, so these are the layers around the cell walls also. These are the walls. So we need these inflation layers to get a good, a reasonable estimate of the pressure forces. And then let's just rotate this around. Hit Z. So this is the mesh refinement. So unfortunately we can't refine this mesh any further. So let's get cracking with the CFD simulation. So let's just save this, write the mesh, call this building example underscore VOL volume mesh. And then there's this option to switch to solution. So you can see that there's a seamless transition from Spaceclaim where you use this button to get it into the meshing mode, and once in the meshing mode we can transition into the solver mode. I tend to use this option called default graphics console. So I have the setup tree where uh, I have the different options to set up my problem, and then I have my console, which is where the software is giving me messages. So this is like the software is talking back to you through the console. If there are any errors or any inconsistencies, it will be printed in here. And this is my graphics. So let's just draw the mesh. So let's just do save display. So that's my building. So that's my building with so I can change the um, look and feel of this building. So I'll just leave it as white. Okay, that's my building. And then there are the balconies, the ground, the podium, and the roof. So these are all the where's my balconies? So that's my building. So what I will do is I will just click on this ball, and then that'll give me a um, isometric view. There's an option to save those views. So click on save. Actually, there's this isometric view. So you can double click. You can flip between back, bottom, front, isometric, left. So you can do that. So right now, let's go back to isometric view, and let's just call this mesh faces, save display. And then what I'll do is I'll quickly set up the simulation. For now, I have the SST omega model as the turbulence model, because I'm not considering any other physics. This is enough. And air, I have the materials where air is a constant density gas. That is fine. We will use inlet flow velocity of about 10 meters per second. So it doesn't look lot a lot 10 meters per second, but trust me, if you are in a 10 meters per second flow, you'll have difficulty in standing up. So before I start running, I'll just create a surface report or a force report to understand the drag generated by this by the building. So I'll select the balconies, the podium, and the roof. Okay, I, and then the enclosure. So that's the surfaces of the building, and the force I. So let's just draw the inlet first to know which. So add to active window. So that's my inlet. So flow is coming from the in the positive z axis. So force vector has to be z, and then call this drag force. Okay, and then click compute. Right now it says solution not initialized, but that's fine. So click OK. So that's my, or just click on drag force and OK. So that's my drag force. So if it flatlines, I can stop running the simulation. So I think I'm good to go. I'll first initialize the simulation. I'll use this hybrid initialization, which will solve like a simplified version, like a potential flow equation. And once that is done, there's an advanced initialization that you can do, which is called FMG. And this is like a quick search bar where you can look for different commands. So if you just search any command like display, it will show you like the options here, and also like a text user interface where you can look for any information that you want. So FMG initialization is like an Euler equation that is solved for this problem. And this Euler equation, it takes a little while, but it should give us a much better answer. So what I'll do is I'll solve it for say 50 iterations or 100 iterations, and then explain how we can post-process the simulation. Okay, so it says converge, converge. So that's all good news. If it didn't converge, it would give you errors with a different color. Let's just look at the contours of pressure on the balconies, enclosure, the ground, and the podium and the roof. Click save display. So that's my actually, maybe let's look at like this. So what this is saying is, let's just add views. One trick I can show you is, so click on this Z and look so that you see this in head on. So there's an option to change to orthographic or perspective. So orthographic is projection, and then use your mouse wheel to rotate so that it's almost at 45 degrees, and then pull it down with the rotate option. So that will give you a very nice viewpoint. So it looks like it's a very nice viewpoint to see. So let's just save this view. Click save. Uh, yeah, I'll just overwrite the isometric. Okay, so next time I want isometric, it will show me this. So here what it's saying is this red regions are regions of high pressure, and then the green regions are regions close to zero pressure, and then the blue regions are regions where you have low pressure. There's an option to change the color map. So here what I can do is I can set field pressure and click apply. And what that has done is it is um, changed it to be just between red and green, sorry, red and blue. So that way you can see regions of high and low pressure a bit better. So that's my contour pressure, and then click save display, and then let's just run the calculation. So for say 100 iterations. So I'm using all the default settings like solution methods and controls. They're usually reasonable. So let us run it for 100 iterations, and in the meantime I will look at any questions. Okay, is it possible to go through documentation to see which models? Yes. So if you go to Ansys help, and what that will do is it'll open up Ansys portal. So you need to have Ansys installed in here, and you can access all this documentation. Okay, so if you click on Fluent, you have, and this is free with any student download. This is you can just change the release to be an older version. And then you have a lot of tutorials here. You have a lot of videos that show you how you can use Ansys for doing different things. This is where the documentation is. So if you look at user's guide or theory guide is how the equations and how the models are implemented into Fluent, and then the user guide is how to use those models, what to turn on, what are the criteria to check. Okay, so let's look at any other questions. So then how do you, okay, is it possible, okay, how do you compare CFD and wind tunnel tests? That's a very good question, Ulysses. um, it is possible to compare CFD and wind tunnel tests, but you need like a full version, like a soft commercial version of the software, where you keep refining the mesh until you achieve the results from the wind tunnel. But yeah, there are companies who do wind tunnel tests and also CFD analysis, and people, obviously they will do these internal benchmarks. So for suppose you're doing a wind tunnel test, what you would do is you would look at, so you would create like you could create measurements of pressure at different locations on this building, and then you would have the same locations in CFD, and you can get like an area average pressure there in CFD and compare the two. You can do things like that. Okay. um, any criteria for considering the number of iterations? You have to ensure that it converges. Right now, because we are short on time, I'm just running it for 100 iterations, but ideally you run it until residuals drop by 3 orders of magnitude, or this drag force plot kind of flatlines. You see this big evolution, that's because the flow is still establishing itself, but then these oscillations should go down and then flatline pretty soon. Next question, which is using this software? So maybe that's a question for Lisa. Or so I think remote labs would have access to the software. But okay, let me just do Ansys software download, and then if you click on this student version, and if you go to Ansys student free download now, so you can just download this version. So I'll paste this link everywhere or in the chat, so that you can. Okay. How can we determine the wind direction in a new building? Usually, there's like a climate study that is done, Augustine, and that climate study will tell us what is the tendency of the flow, which direction it will come from, what speeds it will come from. Usually, they monitor this weather over a long period of time to get that answer. Okay, so and then based on that, especially when you're building a new building, you want to orient it such that it doesn't cause undue flow acceleration or flow deceleration. So if it causes a lot of flow deceleration, it will be subjected to high loads, and if it allows lots of flow accelerations, it might become uncomfortable for people to walk around that. Okay. um, Actually, then what heights are the uncomfortable these the floors used for? I think they are left empty, but I'm not 100% sure. You can probably do a bit of reading and then see what they are used for. But yeah, I thought it'll be something interesting for you to do your own research into. How do we know that the building is capable of withstanding these pressures? So you do a structural analysis. So if it gives you the forces and moments, you then get the forces acting on the geometry, and you choose the appropriate materials for it. Okay, so that's how you do. um, how can we determine the wind direction? I think I've just answered, Augustine, your question. You have to look at climate analysis. So, and that's a whole new topic, which we don't have time for. Okay, so that's our 100 iterations done. So there are some warnings saying viscosity ratio is limited. That is usually um, seen in such large buildings. You see that residuals have not dropped. Ideally, I would run it for 500 iterations, but you see this kind of a pattern emerging. If you run it for another 500 or 400 iterations, you might see this repeat itself, which means it's like a it's like a shedding pattern that is happening. Okay, let's just save this case in data before we do anything about this. So just call this CONV for converged, because if it yeah, so that's where we are. So let's look at the pressure contours again. Click display. So you may notice it, but if you go back into the video recording, you might see that these areas were not there before as low pressure regions, but they are now. Also, you can change the color map options to be a bit better, like 7.66 e power minus 1 is not as interesting to read as float like 77. And also you can change the color map to be 10, so that and then click banded, and then that show you different bands. And also you can change the range to be from um, minus 200, or maybe minus 100 to be 100. Okay, so you can do something like this. So it's showing where it is between, so this region is between 80 and 100. So this region is between 80 and 100. The slightly lighter region is between 80 and 60. This is between 60 and 40. Then so on. So this way you can see which regions are um, so this region has the lowest pressure, and you see that that's between minus 80 and 100 pascals. Okay, so that's my pressure contours. Now if we want to look at velocity contours on the surface, the velocity contours won't make sense. So what we do is we need to create a surface that is offset uh, by about 1 meter or 1.5 meter from the ground. So let me just click new and then surface. There's an option called transform. What I'll do is I'll just take the ground and transform it in the y direction upward by say 5 meters. Usually it's about 1.5 meters, but just for now I'll just do just call this transform hyphen ground and click create. And what that will do is you can copy create a new one, and then this time look at velocity and then look at this transform ground, click save display. And so you see this again will change the color map options, and once you do it once, it will it will remember itself. So just change this color map size to be 10, apply, close, and then banded, and remove this, set this to be 15 meters per second. Okay, or maybe 20. So um, recall that our inlet velocity was 10 meters per second, but if you see in the this this region, it's between 12 and 14 meters per second. So 20%, 20 to 30% increase in the flow speeds. Okay, and even here, that is also between 14 and 12 meters per second. So that's like a 30% increase. Let's just, I'll show you how you can combine different things. So let's just call this contour velocity, click save display, and then I can click on velocity contour and mesh faces, and then I can give like a transparency to the mesh faces, and then you can rotate it around and look at this. So one of the things I said is we need a very large domain around here, and the reason we need it is, you see this blue region where the flow is really slow, that's all the wake of the building. Ideally you want to have a big enough domain that this wake dissipates itself. Right now we are truncating this wake, which is not ideal, but because we don't have any more cells to play with, that's what we have done. But yeah, you need a much bigger mesh to capture this wake properly. But that's your velocity magnitude. So you can clearly see that, suppose you have a door here and a door here. Suppose these were two office towers. If you had something like this and the flow was coming straight on like this, people would face a lot of difficulty walking. Suppose suppose you put a canteen here for people to have like a lunch or something. Unless you have mitigation measures, they'll not come here because it's too windy. You can't sit there and eat. Okay, so things like that. So even here, so whereas here if you put that, it's the same canteen, if you put it here, people can spend a lot of time here because it's much calmer here. Same here and same here and same here. Okay, so you can also look at the you can do the transform on other surfaces as well and look at the velocities. Okay, so let's just save this again, and I have another 3 minutes. Um, and what I will do is I'll just show you how to create path lines. So what I'll show you is how to what's causing this flow acceleration. Okay, so what I will do is I'll just create a line, and then just call this line -1, and then click on select points with the mouse, select this, and click create, and then click path lines new, and I'll use this line 1 and set this to be a fine cylinder, and set this to be 1 meter thick, apply, and then put color them by pressure. Okay, path lines forward, so this is telling um, how the flow is moving from that line. I can then copy this, and then there's this option to reverse the path lines, and this is showing where the flow came from to get there. Okay, so if I go to the scene again, I can switch on both these path lines forward and backward. Only thing is I can close this, I can close this. So what that is showing is, you see this fast flowing air, this is high pressure air, so because I'm coloring this with pressure, so it hits the building and gets diverted. See, it gets diverted because of the presence of the building. Before this building was there, this would just go straight. Okay, right now it's having to move around, and what that is doing is there's flow coming in here, which is also going that way. So let's just do another line. So new line, cancel, new line, and then call this line 2, and then select with the mouse, select this, and then create. And what I will do is so you see that let's close this, or let's just leave it like that. So you see that, see how the flow is getting pushed around, and if you do similar here, you will see that the flow is getting pushed around from its original path by the building, and that's creating these localized pockets. So if there were streets here and you were moving around the building, you would avoid this through experience. You'll see that, oh my god, it's so windy over here. You'll stick closer to the walls maybe. Okay, so that's how you can post process the simulation and then understand the flow patterns. I think that brings me to the end of the session. Um, okay, so let's see. Um, can you apply vortex, Yavuz? Um, there is vorticity included in the governing equations. You don't have to apply it specially. Okay. Um, yes, in the densely built areas, wind will automatically reduce, but then there'll be some regions where flow will get channeled. Like for example, here you see this, there are two buildings side by side, and that's pushing air into this small region. So you'll see regions like that. You'll see that localized wind accelerations. Um, yes, you can, Liana, you can look at different types of geometries and see which one is giving a better or having a smoother pressure force on the or variation on the building. But it's you have to do multiple tests for that. Um, yes, you can do different wind load directions. Abdul Nazir is just going to take too long. I've just shown you how to do one. You can just repeat this analysis for other ones. Key factors for mesh generation and turbulence modeling. Right now, if you're using Ansys Student, I think right now it's the limitation of the how many cells you can have. But if you have access to the full version of the software, you just need to refine like the balconies with 5 or 6 cells that also have at least 10 cells across like the building facades. So for example, between this surface of the building and then this surface of the building, you should have at least 10 inflation 10 layers, 10 cells to get the correct pressure resolution. Okay. uh, Then how can I determine yeah, so if you want to look at forces acting on the leeward and windward sides from the software, that's a very good question, Brian. What you have to do is you just create, right now all the building walls are connected as one surface, but you can select the windward and leeward sides and create a new name selection, and then you can track the forces and on them. So that's a very good question, Brian. Thanks for asking that. um, okay, Manhattan was. Do you have areas? It's just something that I've know. I've. It's like a story that I've heard from others who have been around in Manhattan. It's because there are these long, there are these tall buildings, and then long, and then the flow either has to go around all the buildings or it has to squeeze through those buildings. So when it's through those buildings, you will find that some regions are windy when compared to the others. Um, which part of the building is ideal for measuring acceleration? Wow, Osman, that's a very good question. Generally, it will be the top. The as you go up the buildings, the accelerations will be higher. Looks like you know your civil engineering, so hopefully you found this interesting. Um, measure wind effect on the durability of a building. There are special CFD studies that can give you um, some advice on that, but I think right now we are running out of time for me to go into that in a lot of detail. But you can do your own research if you are interested, and you should be able to do that. And then Solomon, I used Ansys Fluent software for this. I think if you scroll up the previous messages, you can find the link to download the software. Maybe I'll share it with Tina as well. Um, okay, I think I'm done with the questions. Also, I also have another tutorial at EIT to go to right now. So probably what I'll do is I'll hand it over to Lisa. Thanks again, Lisa, for your patience, and I'll see if I can sort out my mic issue for next time. Thanks so much, everyone. I'll hand over to Lisa,
Thank you,
and I'll stop
Mr.
sharing.
VJ, for that. And I'll go ahead and just take over now. So, guys, thank you so much for attending, and I hope that all your questions were answered. I did take notes, but it seemed that he already answered your question. So, I hope everything was fine. So, before I share you the link and the QR code shortly, let me just I'll let you know that we have the following courses for our upcoming intakes. We have professional certificate of competency courses. They are short courses and they are offered all throughout the year. We also have diplomas and advanced diplomas also offered throughout the year. Can just go to our website for that. Our undergraduate and Bachelor of Science degrees, our undergraduate certificates rather and Bachelor of Science degrees would have an intake on the 24th of July. Graduate certificates and Master of Engineering degrees on the 26th of June. Doctor of Engineering, 24th of July, and all our on-campus higher education courses from bachelor's, master's, and doctors of engineering programs would be on the 31st of July as well. And we also have upcoming webinars. We have the low voltage switchboard design and construction verification. That would be next week, Wednesday, the 12th of April from 3 p.m. to 4 p.m. We also have the basics of process control and loop turning. It's a repeat webinar. So that would be from 3 to 4 again. That's on two, I mean, once next week or the week after next week. That's Wednesday, the 19th of April. So if you want to access all our future webinars and events, just go to www.eit.edu.au/news-events/events. And for those who'd like to request for their webinar certificates, you can use the QR code here. You can scan it, or you can also use this link. I will paste the link in the chat box. And please take note, guys, this is very important that you would request for the certificate using the link or the QR code, fill out the form in there, and please do so on or before Sunday evening so that you won't go past the cutoff. If it's already past the cutoff, we may not be able to issue the certificate or give out the certificate anymore. Okay? So just go to that link or scan the QR code, and that would be as easy as that. All right? So if you don't have any more questions, I'm sure that Mr. Vijay had answered all those questions. So thank you so much, guys, for attending. We highly appreciate it. Hope that we will see you in our next webinars. And if you'd like to contact us, you can go to our website. For those who are in Australia, you can visit our head office. The address is there on the screen. You can also call us if you're inside or outside Australia. The numbers are there on the screen. You can any concerns about webinars, you can send an email to webinars@eit.edu.au, and you can go to www.eit.edu.au/schedule for all our courses that are scheduled for this year. Thank you, guys. May you have a great day and a great weekend ahead for those who are having long weekends. And that will be it. See you soon.